morning, ladies and gentlemen. I'd like to welcome you to the third part of the InfiniBand Trade Association Fall Webinar Series. InfiniBand technology, no magic, just good engineering. Today we are using GoToWebinar for the presentation. Before we get started, let me call your attention to the control panel at the top of your screen. We encourage you to ask questions at any time by clicking Enter a Question for Staff on the control panel. Depending on how much time we have, we'll try to respond to selected questions either during our discussion or at the end of the session. If we don't get to your question, we'll answer them offline afterwards. Today's conversation is being recorded, so if you lose connection or run into technical problems, the whole webinar will be available on the IBTA website. Now, with the logistics out of the way, let's bring back our two panelists. Paul Gruen is Chief Scientist at System Fabric Works and has worked for more than 30 years on server I/O architecture and design, and was a member of the original InfiniBand architecture team. He is still involved in the Open Fabrics Alliance and is a director of the InfiniBand Trade Association and an active technical contributor. Jim Ryan is chair of the Open Fabrics Alliance, an organization that develops, tests, licenses, supports, and distributes Open Fabrics enterprise distribution, an open source software to deliver high-efficiency computing, wire speed messaging, ultra-low microsecond latencies, and fast I/O. He is also a manager at Intel and has been with Intel for more than 10 years. Good morning, Jim.
Good morning, Rachel, and thanks for that kind introduction. And good morning, Paul.
Hi, Jim. Good to see you again. And good morning and welcome to our audience.
In our first two conversations, we raised some questions about the role of I/O in the modern data center. In the first webinar, we talked about how something as basic as I/O can play such an important role in how the data centers evolve over time. And we also observed that I/O architecture seems to be advancing along two trajectories. One trajectory is sort of the steady march and well-known technologies along a regular evolutionary path. For example, the steady drumbeat of continuous improvement in network speeds or the emergence of new and improved forms of PCI. The other trajectory is almost like a quiet revolution and represents a more fundamental change in the way that applications do I/O operations. Remote direct memory access, or RDMA, is an example of this kind of quiet revolution. It's a technology that's been proven in the market for quite a while now, something like 10 years or more, but until recently has been viewed by many people as a niche technology that is really only applicable in high-performance computing and specialty applications. In our first discussion during the September webinar, we offered the hypothesis that adopting a technology like RDMA can be very helpful to IT technologists in helping them keep ahead of the curve, and the thoughtful application of interesting new technologies can indeed be a useful tool in the IT technologist's toolkit. All of that sounded really good, so in our second conversation, we talked about some practical strategies for taking advantage of this quiet revolution in I/O. We talked about some specific ways we can keep our data centers up and running while also allowing a smooth transition forward. In other words, there's no need to throw the baby out with the bathwater while we work on improving our data centers. Again, this is all really great stuff, but honestly, some of the claims we made about the capabilities of RDMA and the amazing and wonderful ways it can transform the data center have a certain sort of black magic feel to them. So I thought it would be good to take this opportunity to pull back the veil a bit and try to demystify some of the black magic. Way back in the first webinar, we described a set of 3 figures of merit that figured into the motivation for creating a new I/O architecture. Those figures of merit were application-to-application latency, CPU utilization, and bandwidth. But since the first webinar, we haven't really gone back and described how the RDMA architecture receives these figures of merit. So I'm thinking for this webinar, it might be a good idea to see if we can explain how the RDMA architecture achieves these magical capabilities.
Well, that's a good idea, Jim. I think it does make sense to peer under the covers just a little bit. So let's peer a bit into the details of the architecture and see if we can back up these claims about improved latency, reduced CPU utilization, and better bandwidths, the 3 so-called figures of merit. We said during our first webinar that achieving the 3 goals that RDMA set out for itself required a rethink of the whole idea of I/O. That rethink also meant we had to jettison a lot of conventional thinking about the way I/O has always been done. Well, it turns out that most of that rethinking and jettisoning occurred during the development of an earlier architectural concept called the Virtual Interface Architecture, or VIA. VIA, which most people have probably never heard of, emerged during the late 1990s, and it wasn't just an academic exercise in improving I/O. It actually had a very specific goal in mind, which was to improve the scalability of clustered systems. The observation then, and it's still true today, was that cluster scalability is inversely proportional to latency. So if we could lower the application-to-application latency sufficiently, then clustered computers would be able to scale up to much larger sizes. As it turns out, achieving lower latency also led to some pretty significant improvements in other important characteristics. For example, it resulted in reduced CPU utilization and a reduced demand for system memory bandwidth. In turn, this entire set of characteristics led to a host of goodnesses, many of which we talked about in our first two conversations. So the whole process of rethinking the I/O problem meant re-looking at how applications communicate with other applications, with the implication being that I/O should really be looked at as an end-to-end problem. It would certainly have been possible to gain some incremental performance improvement by accelerating the wire bandwidth or by improving the network stack or by some other piecemeal approach. But it's pretty clear that major improvements are only going to emerge if we give ourselves the freedom to invent a solution set that incorporates the whole environment from application to application, or if you prefer, from end to end. That meant looking carefully at all the links in the I/O chain connecting two applications together. And more importantly, it meant looking at how those links related to each other. In other words, I/O is in fact a systems problem, because at the end of the day, what matters isn't the wire speed or better adapters or clever routing algorithms. What matters is how the application actually performs in the real world. So one of the key learnings from the VIA project was an understanding of one of the principal causes of latency in traditional I/O systems. For reasons that I'm pretty sure we all understand quite well, traditional I/O operations depend pretty heavily on the kernel. In fact, the kernel sits directly in the I/O data path. As we learned during the VIA project, if we really want to avoid latency, we have to find a way to reduce or eliminate context switches into kernel space, which means that we have to remove the kernel from the I/O data path, and we have to make it possible for an application to do I/O operations directly from user space without trapping into the kernel. To do that, let's hypothesize the existence of a new service that we'll call an I/O service that allows an application to communicate directly with another application, but doesn't rely directly on the kernel. If such a service were to exist, what would be its most important characteristics? Well, since the purpose of the new I/O service is to allow applications to communicate with one another, and since applications typically communicate by exchanging IPC messages, let's start with the assumption that the I/O service should be based on message passing. As it turns out, that makes a lot of sense for another reason. A traditional network, like a socket service running over TCP/IP Ethernet, is based on transferring streams of bytes. This meant that bytes are streaming in off the Ethernet wire are placed in an anonymous buffer residing in kernel space. It then becomes the kernel's responsibility to determine to which application the stream should be delivered, which it does by examining the packet headers. The receiving application, in turn, provides a receive buffer, and the kernel copies the stream into that buffer. Since the byte stream doesn't carry with it any notion of messages, it falls to the application to examine the byte stream and locate the messages contained within it. All of that consumes time, it consumes CPU resources and system memory bandwidth, and it adds to the latency, which is exactly what we're trying to avoid. So unless we want our new I/O service to simply replace the OS and spend its time receiving byte streams just as the OS would have done, we probably ought to build the I/O service around message passing. In recognition of that fact, let's change its name and call it a message service. We said that our new message service has to be able to allow applications to communicate directly. The best way to do that is to make it possible, under controlled circumstances, for an application to directly read and write buffers in another application's virtual buffer space. In fact, the other application is actually in an entirely different physical address space too. That's exactly what we mean by the expression remote direct memory access. So let's change the name of our message service one more time and call it an RDMA message service, a service that allows an application to place messages directly in the virtual address space of another application. Naturally, one application can't willy-nilly access another's virtual space without creating havoc, so we'll take it as a given that the RDMA message service provides appropriate isolation and protection services, at least as good as the OS would have provided in a conventional I/O architecture. This is done by an address translation feature that's part of the message service. We'll leave the details of how that works as a topic for another day. So since we want this message passing service to be accessible directly from an application's virtual user space, we have to provide some sort of an interface to it. We'll call that interface the software transport interface. So the first order of business has to be to define some kind of a data structure that can be mapped into an application's virtual address space. In the RDMA architecture, we'll call that structure a Q-pair, or a QP for short. The QP is the logical structure that applications use to access the RDMA message service. Since a QP is a logical structure that exists in memory, there can be a very large number of these things, and an application can use as many as it needs to communicate with as many other applications as required. In other words, the QP space is virtually unlimited. But because the Q pairs exist in physical memory, the address translation feature is used so that when the application writes to a Q pair in its virtual address space, the actual write occurs in physical memory and is therefore visible to the RDMA messaging service, which operates in physical space. So the Q pairs exist in physical memory space and are mapped into the application's virtual memory space. So to use the RDMA message service, all an application has to do is to post a work request on one of the Q pairs. Each posted work request represents a request from the application to the message service to either transmit or receive a message. Once the application has posted the work request, it's free to go off and do other work. Once the message queue transfer is complete, the message service puts a notice on another set of queues called a completion queue, and that concludes the message transfer cycle. This idea of posting work requests frees the application from having to concern itself with the mechanics of posting or receiving streams of bytes. Once it has posted a request to the work queue, it can go off and do other useful work without waiting for the message transfer operation. In other words, the software interface is fully asynchronous, shown by these little funnels in our picture here. So by creating virtualized Q pairs and by defining a message as the discrete unit of work, and by defining a mechanism for the RDMA message service to notify the application when the work is done, we've pretty much met our goal of allowing the application to carry out I/O operations directly. By giving the message service a virtual interface that maps directly into the application's user space, we eliminate the need to make kernel calls for I/O service. This in turn is instrumental in dropping end-to-end latencies down into the very low single digits, typically less than 1 microsecond from application to application. By creating a message service, we've eliminated the role of the OS in handling streams of bytes. This significantly reduces CPU cycles that have to be dedicated to I/O operations. It's not at all uncommon to see CPU utilization during I/O operations drop from something like 25 to 50% down to almost zero. In other words, we've removed the kernel from the I/O data path. And finally, since the message service knows how to place inbound messages directly into an application's buffer space, we completely avoid the need to copy inbound messages into an anonymous kernel buffer before delivering them to the application. This means that we don't have to consume valuable system memory bandwidth copying messages between kernel space and user space. So we're beginning to see some pretty significant differences between the way a byte stream of data is transmitted through a conventional sockets interface compared to how a message is transmitted using the RDMA message service. And one question that may be emerging for some folks is exactly how an application does these things, like create a Q pair or post a request to a Q pair. Well, that's all done through the magic of an API designed specifically for RDMA called the Verbs API. We'll talk about the Verbs API in a couple of minutes. So simply put, by building our I/O architecture around the notion of a message, we can define a message service that's capable of fetching a message directly from the sending application's buffer, transmitting it across the wire, and placing the message directly in the virtual address space of the receiving application. And that's how it works.
So that explains why we've been calling it an RDMA messaging service during the past 2 webinars. That actually begins to make some sense.
Yeah, exactly. It does make sense. When you boil it down in terms of what an application really requires, it isn't interested in the mechanics of transmitting streams of bytes. What it really needs to do is to send messages, where a message is some unit of communication that is meaningful and significant to the sender and receiver of the message. From the application perspective, transactions across the wire get much easier since the application no longer has to sort through piles of bytes that arrive in its input buffers in order to find the beginning of a meaningful piece of communication, like a message, for example. So right off the bat, by designing the RDMA architecture around messages instead of around byte streams, we've simplified things from the application's perspective considerably. And as it turns out, we also end up simplifying things tremendously for the transport protocol too. And that's how we lower latency and improve performance. Well, okay, so far so good. But we still have to provide a mechanism for physically moving those messages across the wire. And for that purpose, the InfiniBand architects designed a transport service which could be used for that very purpose. And since it doesn't have to concern itself with byte stream traffic, it can be tuned for optimal performance when transporting messages. So we know right up front that the InfiniBand transport has to be message-oriented. Because the InfiniBand architects realized that an application would likely have requirements for transferring different types of messages, they gave the architecture two different ways of transferring messages, called a send-receive operation and an RDMA operation. We also sometimes call the send-receive a channel semantic because it works like a classic I/O channel. The sender pushes the message to the receiver's message service, which is then responsible for placing the message in user memory. This is really helpful for small message operations like control messages or for exchanging synchronization messages back and forth. By contrast, the RDMA operations are sometimes called a memory semantic because the initiator of the RDMA can directly read or write the virtual memory of the receiving end without involving the receiving end in the transaction at all. All the receiving end has to do is to let the initiating end know the location of the destination buffer. Once that's happened, it isn't involved in the actual transfer of the data. One common use for an RDMA operation is to transfer larger blocks of data. Like in a SCSI operation, for example, the SCSI initiator merely lets the SCSI target know the location of its data buffer, and then after that, the SCSI target can do RDMA operations to read or write data into the initiator's buffer until the SCSI data block has been transferred. One other thing I should mention that the IB architects did. Traditional IP networking provides two different services called TCP and UDP. TCP is called a reliable connected service, and UDP is an example of an unreliable datagram service. In a similar way, InfiniBand's architects gave it a couple of different types of service. Just like the IP suite, they provided a reliable connected service called RoCE and a datagram service called UD. And they also provided a couple of other services that might be useful in transferring messages, but we'll leave those out of scope for today.
Paul, one thing I've never understood, since IB has services that are so similar, why didn't InfiniBand just go ahead and use the TCP transport? It's there, it's standardized, and has been shown over the years to be tremendously rugged, and everybody understands it. Why go to the trouble of defining a new transport service?
You know, that's a really good question. There are really two answers, two reasons why we chose to create a new transport. One is because of what we've been discussing. TCP is designed to transport streams of bytes, while the InfiniBand RDMA architecture is supposed to be message-oriented. The way you provide reliability guarantees for a byte stream is much different than the way you would do it for a messaging protocol. So if we had simply adopted the TCP protocol, it would have been necessary to define some kind of a construct on top of TCP that would have let us find the boundaries between messages. That would be necessary so we would know how to deliver a completed message to the receiving application. But unfortunately, there's really no easy way to do that. In the end, it turned out to be much simpler to define a transport protocol that knows how to deal natively in messages. Let me give an example. For a reliable transport protocol, you have to be able to detect and recover missing information. If you're looking for missing bytes in a byte streaming protocol, you have to keep track of windows of outstanding bytes on the wire at any given moment. And you have to be able to back up in that window if you find out that bytes are actually missing. But with RDMA, because we know we're always dealing in messages, all the transport protocol has to do is to keep track of the messages that are on the wire and not the individual bytes. If a message gets lost, it's a relatively simple matter to resend the missing part of the message and to do so at full wire speed. So the basic reliability mechanisms for detecting and recovering missing information really become much simpler in concept and therefore much easier to implement in hardware. The other reason why TCP wasn't used is this. TCP is designed to work with Ethernet as its underlying physical wire, but Ethernet is classified as a lossy wire. Now that's not a pejorative expression, it just means that in the normal course of affairs, an Ethernet switch will normally drop packets as a way of signaling to the endpoints that they need to slow down the injection of packets onto the wire. So when TCP detects a missing byte or packet, it slows down, backs up a little bit, and begins retransmitting packets, usually using something called a slow start protocol. Since our target when defining InfiniBand was to achieve the lowest possible latency, the InfiniBand architects decided very early on to define a wire that would not result in dropped packets. We call that a lossless wire. Again, the expressions lossy and lossless aren't value judgments, they're just names for certain kinds of wires. So by deciding to build InfiniBand on top of a lossless wire, the transport protocol design became greatly simplified and significantly faster as well. So apropos to reducing end-to-end latency, there's one more small point that I should raise because it's relevant to removing the kernel from the I/O data path. I said a few minutes ago that TCP and the sockets interface rely on the OS to receive inbound packets and determine the ultimate destination for those packets. Well, since we've been talking about removing the kernel from the I/O data path, people might be wondering how these inbound messages get delivered to their intended destinations if there's no kernel in the path to look at the headers and deliver the packets instead. The answer lies in the queue pairs I described a little earlier. I described a queue pair as the mechanism that the application uses when it wants the message service to transmit a message. We said that the application posts a work request to the queue pair requesting message transmission. The same thing is true of receiving a message. An application can post a request to receive a message on the queue as well. Then, when an inbound message arrives, the RDMA message service knows exactly where to put that inbound message. By pointing a message at a particular queue pair number, you're actually also identifying the final destination for that message in the application's virtual memory space. So not to confuse the issue any, but it's sometimes helpful to think of the queue pairs as forming the endpoints of a channel between two applications. This idea of a channel is an important part of achieving our overall goal of eliminating the kernel from the I/O data path. Once the channel has been established, the two applications are free to use it without requiring further involvement from the kernel. It's another example of how the best way to achieve really great application level performance is to look at I/O as an end-to-end system level problem.
So I think you convinced me that the RDMA architecture reduces application-to-application latencies by eliminating the kernel from the I/O data path, and that we can dramatically reduce the burden on the CPU by moving from a byte streaming protocol to a message-based architecture, and that we can conserve our valuable memory bandwidth by completely eliminating buffer copies as part of receiving incoming messages. What about this business of a verbs API?
So that's a good point. I'm glad you brought it up, and I threatened earlier to discuss that, and let's do that right now. The question of the so-called verbs API comes up often. This API is the programmatic interface that an application uses to access our RDMA message service. Remembering our slavish devotion to looking at the I/O problem systemically, and given what I've said so far about how the RDMA message service works, we start to get a picture of the requirements for so-called verbs API. In fact, if you look at some of the design characteristics that I discussed earlier, these define a pretty clear set of requirements for the verbs API. In the same way that the sockets API is designed to work with a byte streaming sockets interface, so too the RDMA architecture has its own set of APIs called verbs that are specifically designed to work with the RDMA software transport interface. So let me give an example of this. One of the keys to RDMA performance, and one area where it differs pretty dramatically from sockets, is in the way it receives inbound packets. In the case of RDMA, inbound messages don't ever arrive unexpectedly. Part of the whole process of receiving an inbound message is to post a work request on the queue so the message service knows where to place an inbound message when it arrives. But first, there has to be a queue pair to post that request on. Fortunately, there are so-called verbs designed for those very purposes. There's a verb for creating a queue pair, for creating a connection between queue pairs, for posting work requests on the queues, and a host of other reasons. And hopefully that gives a little bit of insight into the notion of verbs in the Verbs API. So again, in keeping with the basic requirements established for RDMA right from the get-go, application performance first and foremost. And that singular focus on applications, in turn, drove the requirement for a message passing architecture that could be implemented without relying on the kernel as part of the data path. It was in that same vein that the verbs were architected and which drove the subsequent development of the Verbs API. Hey, you know, Jim, since we're on the subject of APIs, and since you're part of the Open Fabrics Alliance, maybe this would be a good time to talk about the Open Fabrics Alliance role in providing software for InfiniBand.
Good idea, Paul. I never pass up a chance to talk about OFA. The OFA was formed with the idea of providing open source software that would help drive adoption of RDMA technologies. In that vein, the OFA supplies the complete software stack needed for an RDMA implementation. Even though this is an InfiniBand Trade Association webinar, I think it's useful to point out that the OFA software supports all forms of RDMA, including not only InfiniBand and RoCE, but also IWAR, even though it's a little out of scope for today's discussion. The important point that needs to be made for today is that there are complete software solutions available in open source needed to support RDMA technologies. The Verbs APIs, of course, are crucial in writing applications that run over an RDMA network. But beyond the Verbs API, remember in our last conversation we talked about a set of upper layer protocols, or ULPs. One of the ULPs that we mentioned was called SDP, which stands for Sockets Direct Protocol. This ULP, which sits conceptually above the Verbs API, lets a native sockets application run over an RDMA network. Naturally, you sacrifice quite a bit of the end-to-end application performance we've been talking about, but nevertheless, there may be situations where you really want to deploy RDMA, but you also have to accommodate some existing legacy apps.
Well, Jim, you know, I'm a hardware guy, so this whole concept of developing software is kind of like black magic to me. If I were a software developer, I might be tempted to think writing an application to the Verbs API is a pretty daunting task. But I happen to know that there's some help available, and I really don't think our audience would mind if we took a minute to describe that.
That's just too good an opportunity to pass up. It just so happens that the Open Fabrics Alliance does offer a pretty good course called Programming with Open Fabrics Software. It goes through the whole process of writing an application to the Verbs API. So that's one obvious way to get started. And of course, since it's all open source, there's also a vibrant community of developers and like-minded souls all eager to help.
Well, that's great. So what that means is that there's really no excuse for not diving in head first while being pretty sure that you're not going to wind up with a serious concussion. So let's move on and complete the picture of the RDMA architecture by addressing the last part, you know, saving the best for last, so to speak. Okay, so we've talked a little about the so-called RDMA message service and got a glimpse into how it works. Since we wanted to avoid the use of the kernel as part of the I/O data path, we began to see pretty clearly the need for a special interface. Since the message service isn't anything like conventional sockets, it didn't make too much sense to adopt the Sockets API, even though there are a couple of upper layer protocols, like SDP, that can help us in supporting legacy applications. So a new API, called the Verbs API, was created from the ground up to match perfectly with the RDMA message service. And that brings us to the third major component of the RDMA architecture, which is the underlying physical wire. In the same way that the Verbs API was designed to work with the underlying RDMA message service, so too the characteristics of the wire defined in the InfiniBand specs were chosen to work specifically with the RDMA transport layer. One point that we sort of glossed over a bit when we were talking about the transport protocols a couple of minutes ago. Remember how we talked about jettisoning some conventional thinking in favor of a single-minded focus on our desired end goal? Well, early on in the process of developing the InfiniBand architecture, someone observed that the transport protocol could be very efficient if we could make some assumptions about the behavior of the wire. For example, if a wire could be defined that does not allow packets to be dropped, then it would be possible to design a more efficient transport. So think about TCP and an Ethernet wire for a minute. As I think most of us are aware, Ethernet is a so-called lossy wire, meaning that Ethernet switches are designed to drop packets in the presence of congestion in the switch. Those drop packets act as a signal to the TCP transport. The TCP, in turn, knows how to interpret those drop packets and what to do in response. It's a pretty bulletproof design, and it's worked beautifully for decades. And it's especially effective because it works so well across such a broad range of environments, ranging all the way from small home networks to large corporate LANs to the wild internet. So in the same way that TCP works well with the Ethernet wire, so too the InfiniBand transport protocols were designed from the outset to work with the InfiniBand wire. It was actually the inverse, though, since the wire characteristics were chosen in order to make the design and implementation of the transport cheap and easy. So by defining the InfiniBand wire to be lossless, it was easier to design an efficient transport protocol that could easily be implemented in hardware. There's probably one other point that bears mentioning since we're talking about the origins of the InfiniBand architecture. At the time that the IBTA was busy creating the InfiniBand architecture, it also defined a speed roadmap that at the time was substantially more aggressive than anything that could be had off the shelf from any of the existing standards bodies. And that actually made a great deal of sense. The vast majority of the market being served by Ethernet at the time really didn't need the kind of bandwidths and speeds being proposed for InfiniBand, so it didn't really make sense for Ethernet to define an aggressive high-speed roadmap. So that was another reason that helps explain the genesis of the InfiniBand wire.
Okay, but hold the phone. In the last webinar, you mentioned being able to run the InfiniBand transport over Ethernet using something called RoCE. You just said that an Ethernet wire is lossy, but the InfiniBand transport depends on a lossless wire. So how can it make any sense to run the InfiniBand transport over an Ethernet wire?
That's a pretty interesting question that turns out to have two answers. One is the emergence of something called data center bridging, or DCB, and the other is the circumstances under which it makes sense to run the InfiniBand transport directly over our familiar Ethernet wire. But before we talk about the details, let me show you how RoCE works. And to do that, I need to rely on the good old OSI networking stack reference model. I'm really sorry to do this because we've all seen this model a million times, so we'll make it really quick. If you compare the InfiniBand architecture to the familiar OSI reference model, you can see right away that all the usual parts and pieces are there. And I've lumped the bottom two layers together and called them the wire. That's the set of channel adapters, switches, cables, and so on that we can see and touch and are the parts that we've been talking about in this particular section. I've also lumped together two other layers and called them the RDMA part. Those are the parts we were talking about earlier this morning when I described the RDMA message service. I did it this way because the name RoCE stands for RDMA over Converged Ethernet. So those two layers are what we mean by the RDMA part of RDMA over Converged Ethernet. And by the way, don't put too much store in the use of the word converged in the name RoCE. It's really more of a historical artifact than anything else. Our last drawing shows RoCE on the far right. Here's the deal. The only thing that changed was the lowest two layers, the wire. The RDMA part, the RDMA message service doesn't change, including the verbs API. Only the wires change at the bottom of the stack. It turns out the InfiniBand architecture layering is clean enough that it really is possible to simply replace the InfiniBand wire with an Ethernet wire without making any other changes. Oh, and just as a matter of truth in advertising, I should also point out that the fabric management method changes too, since RoCE uses straightforward Ethernet management. I'll talk about that a little more in a few minutes. So that's all good, but it really doesn't answer the question that you raised, Jim, which is how we can use the IB transport with Ethernet. The conundrum is that Ethernet is a lossy wire, but the IB transport was designed to work with a lossless wire. As it turns out, the IB transport, like any good reliable transport, does in fact have the ability to deal with those drop packets, even though its performance might be impacted as a function of how often packets are dropped. So as long as the Ethernet switches don't drop too many packets, everything seems to work out okay. One easy way to avoid packet dropping is to severely over-provision the switches and NICs to try to minimize drop packets and thus avoid annoying the IB transport too much. So even though it might not be an optimal solution, it is in fact possible to run RoCE over today's conventional Ethernet wire. But since we're into optimal results here, you won't be surprised to hear that there's a better way to run RoCE. So you remember I mentioned data center bridging a minute ago? Well, for those who may not have come across DCB yet, it's a new set of standards developed by the IEEE as the next generation of Ethernet. DCB has lots of great features that will make it work really well in a high-performance, multi-stream environment like a modern data center. But the most interesting feature from the perspective of RDMA is something called per priority pause. This is an interesting feature that a switch uses to avoid the need to drop packets as a way of signaling congestion. By using per priority pause, traffic can be slowed down without the need to drop packets. This no drop behavior, of course, makes DCB ideally suited for use with the InfiniBand transport. And by the way, we're not waiting for these DCB-enabled devices. They're appearing in the marketplace now.
Paul, that sounds really great. So with the advent of RoCE, it means that we can now get at least some of the benefits of RDMA while still preserving the familiar Ethernet wire. In our last discussion, you and I talked a lot about the various cost-benefit trade-offs that an IT technologist can make when deciding how to begin deploying RDMA in his data center. So with respect to RoCE, what are some of the key technical differences between the two?
Well, you know, the gap between Ethernet and InfiniBand used to be much wider. But with the emergence of DCB and its ability to convert Ethernet into a lossless wire, that closed the gap somewhat. Even so, there are still two important differences between Ethernet and a native InfiniBand wire. I made a passing reference a minute ago to one of them, and that's the difference in the management paradigms for an Ethernet switched fabric versus a native IB switched fabric. And as always, there will be pros and cons between the two. By management, what we're talking about here is fabric management, how the fabric topology is discovered and configured, how routes through the fabric are chosen, and the myriad other details that are part of making a switch fabric work. The InfiniBand architecture describes what I would call a centralized management structure, meaning that there is a central entity called a subnet administrator, which is a kind of database that keeps track of all the details of the fabric in its current configuration. There's another central actor called the subnet manager, which knows how to optimally configure the fabric. The subnet manager uses the database provided by the subnet administrator to make decisions about how the switch fabric should be configured. So since there's this one all-seeing authority, it means that it can do a magnificent job of configuring switches, selecting routes through the fabric, partitioning the fabric among different users, and a host of other very cool features. It also allows InfiniBand to support arbitrary fabric topologies. But since RoCE uses an Ethernet switched fabric, you don't get the features of IB's centralized fabric management. But you do get a fabric that is capable of configuring itself, and you get the benefit of working with a familiar wire. This may be more than adequate to the task. So the difference in the way the two switch fabrics are managed, there's definitely one important distinction between them, and something that should be considered when one decides how and where to deploy RDMA. And as we mentioned in our conversation last month, there may very well be environments where RoCE is the final destination, and there may be other environments where RoCE is just a transitional stepping stone to a fuller InfiniBand implementation. So besides the differences in management, the other differences between RoCE wires and InfiniBand wires lies in their respective speed roadmaps. RoCE, naturally enough, follows the Ethernet roadmap, while the InfiniBand roadmap is published and maintained by the IBTA. So even though InfiniBand has historically focused on higher speed bandwidth targets, I think that most people have always expected that the gap between the two would close over time, and that appears to be the case today. For example, there are now Ethernet devices available in the market that are capable of running at true 40 gigabit per second speeds, rivaling or even exceeding InfiniBand QDR, which has been the industry standard signaling rate for InfiniBand the past couple of years. On the other hand, the next speed point for InfiniBand, called FDR, which stands for 14 data rate, will be using a newer encoding scheme called 6466 encoding, which means that we'll be able to take full advantage of the wire signaling rate. So again, the choice between IB and RoCE should be based on evaluating the trade-offs between cost, performance, and features. And as we emphasized in our second webinar, you should also consider whether RoCE will be your final destination in the journey to RDMA, or whether it serves as a helpful waypoint deploying a full IB-based solution. Okay, so in 45 minutes we've managed to describe virtually everything contained in 2,500 pages of the InfiniBand specification. Naturally enough, we had to modify our movie a little bit to fit in the running time allowed, but hopefully we've given you some helpful insights into how RDMA works and why it works the way it does. We began today by saying that I/O is really a system-level problem, and that to achieve significant improvements, we really have to look at the overall end-to-end system. We saw that principle in effect a number of times in the way that applications use RDMA to exchange messages. We went a step further and poked around in the details of the RDMA architecture and discovered that its stack bypass architecture is a major contributor in reducing end-to-end application latency, that relying on a message passing architecture helps to drive down CPU utilizations pretty dramatically, and that eliminating the kernel from the I/O data path helped a lot in reducing demand on memory bandwidth by eliminating buffer copies. And finally, we touched on the various wires available that can be used with RDMA. So I hope that by explaining how it works that we've demystified some of the magical claims for performance improvement that are made about RDMA. With any luck, we've made it easier to see how helping our IT technologist friends solve their problems doesn't really take magic. It just takes some good old-fashioned engineering. So naturally, in order to be really worthwhile, any good technology should have a bright future in front of it. And that'll be the topic for next month's installment. We hope to see you all there. So Jim, do we have time for a question or two?
Yeah, we have time for one. Could you explain again what the relationship is between RoCE and DCB? Does RoCE require DCB?
Technically, RoCE does not require DCB, and you can probably get away without DCB. But I think the de facto implementation is with DCB. In order to make RoCE work well in an environment that doesn't include the lossless wire, you have to pretty significantly over-provision the Ethernet wire to make it work well. And that may not be a desirable result in most cases. So my guess is that RoCE will not be deployed in production in other than a DCB environment. Does that answer the question that came in the way you read it?
Absolutely, Paul. Thank you.
Great.
Great. Thank you, Paul and Jim. Ladies and gentlemen, that concludes the third part of the IBTA Fall Webinar Series. Thanks for joining us. If we didn't get to your question during our conversation this morning, or if some questions come up later, we'll be happy to answer them via email. This webinar will be available on the IBTA website, and the next webinar in the series is scheduled for December 9th at 8 a.m. Pacific Time or 11 a.m. Eastern Time. Have a great day. You may now disconnect.